When an organization builds a security architecture from scratch, to achieve native ISO 27001 certification, for example, they face the blank page problem. They must identify every asset, anticipate every threat, and engineer custom countermeasures. This requires months of specialized expert work to derive a baseline that often already exists elsewhere. The German Federal Office for Information Security, or BSI, recognized a structural inefficiency in this approach. They observed that standard business environments face the exact same vulnerabilities universally. Almost every enterprise runs the same basic servers, clients, and network protocols. Instead of forcing every organization to perform a bespoke risk analysis from the ground up, the BSI provides a pre-built, certifiable standard. This framework is IT-Grundschutz, or baseline protection. The heavy intellectual lifting of figuring out which threats matter to a standard server room has already been completed centrally by the authority. Organizations select the building blocks that match their environment rather than starting with a blank page. Early versions of this framework ran into a severe problem. They prescribed highly specific, rigid technical measures. As technology evolved, dictating exact configurations made the framework brittle and prone to obsolescence. To understand how the modernized model fixes this, we have to look at how different frameworks dictate architecture across a spectrum of prescriptiveness. On the far left, native ISO 27001 is process-oriented. It prescribes the method you use to manage risk, giving engineers maximum freedom but resulting in a highly variable final security level. On the extreme right, the old IT-Grundschutz catalogs were measure-oriented. They prescribed exactly how to secure a system, offering standardized results but leaving zero technical flexibility for the implementer. The modernized BSI 200-2 compendium sits squarely in the center. It is requirement-oriented. It prescribes exactly what must be achieved, demanding specific security outcomes while letting the architect freely choose the modern tooling to get there. This paradigm shift gives engineers an auditable blueprint of requirements without locking the organization into specific, potentially obsolete technology. The methodology begins with the IT structure analysis, or structure analysis. This is a comprehensive inventory phase where every piece of hardware, software, and application in the information domain is identified and mapped. In a typical enterprise, this mapping yields hundreds or thousands of individual endpoints. Managing a distinct risk profile for every identical workstation is mathematically and administratively impossible. To make the analysis manageable, engineers apply a concept called complexity reduction. They bundle identical components into singular logical groups, treating a fleet of 500 laptops as one single object moving forward. You cannot group systems arbitrarily. They must share the exact same hardware type, configuration, network connection, and administrative conditions. But the cardinal rule of complexity reduction is this: components with substantially different protection needs must never be mixed. The workstations for human resources, development, or the management board have elevated risk profiles and must form their own isolated groups. If you break this rule and group them together, the framework forces a mathematical compromise. The resulting security level will either vastly overprotect the generic nodes, wasting budget, or dangerously underprotect the highly critical ones. This grouping process compartmentalizes distinct risk vectors, establishing the technical boundaries necessary for a precise security analysis. Once the assets are grouped, we move to the Schutzbedarfsfeststellung, the protection needs assessment. This phase determines exactly how much protection each newly defined object actually requires. The BSI provides 3 distinct categories: normal, high, and very high. Because financial loss means something different to a small business than it does to a multinational bank, each organization must define these thresholds themselves based on custom damage scenarios. When assigning these categories, you encounter a core philosophical rule of IT-Grundschutz. Physical hardware possesses absolutely no intrinsic security value. Protection needs follow a strict top-down inheritance model. Risk flows down the IT stack. The criticality of a business process establishes the baseline. If a process is vital to the organization's survival, that high protection need is immediately inherited by the data and applications required to run it. Only then do the IT systems and the physical rooms inherit their required protection levels. A server is only as critical as the specific applications it supports. When multiple applications share a single server, the system automatically inherits the highest requirement of any hosted application. This is the maximum principle. One highly sensitive app elevates the entire machine. There is a primary exception to the maximum principle, called the cumulation effect, which adjusts protection needs upward when assets are concentrated. Take two mirror database servers. Because they back each other up, their individual availability requirement might be rated as normal. If one fails, the other takes over. But if you place both of those servers in the exact same physical room, you create a shared fate. A single fire takes down both machines at once, destroying the redundancy. Consequently, the room itself inherits an elevated high availability requirement. Infrastructure only warrants defense spending based on the specific payload it carries, or the single points of failure it inadvertently creates. With the risk profile established, the process enters the Modellierung, or modeling phase. Here, the analyzed physical network is rebuilding using the BSI's standardized components. This relies on the Schichtenmodell, or layer model. The modernized framework is function-oriented, splitting the landscape into two categories: overarching process blocks, covering management, organization, and operations, govern the technical system blocks, which handle the concrete infrastructure, networks, and applications. The physical act of modeling involves selecting a specific Baustein, a building block, from the BSI compendium, and logically snapping it onto a target object in your network map. A Baustein is much more robust than a simple checklist. Inside each 10-page block is a specific threat landscape mathematically mapped to a rigorous set of requirements. These requirements are strictly categorized by bindingness. They use highly deliberate modal verbs, mandatory rules you must implement, standard practices you should follow, and optional measures you can adopt. Every single requirement is anchored in the Kreitz reference tabella, a cross-reference table. This grid proves exactly which standardized elementary threats, cataloged as G0.x, are neutralized by which requirement. Modeling ends with a strict completeness check. Exotic technologies that lack a dedicated Baustein, like a specialized lab instrument, must be approximated using closest-fitting blocks to ensure no unprotected blind spots remain. Through modeling, the abstract asset inventory is transformed into a specific block-by-block engineering test plan. That test plan is executed during the Basse-Sicherheitscheck. This is a strict target versus actual comparison between the model's requirements and the actually deployed modelers. Engineers assign one of four implementation statuses: yes, partially, no, or dispensable. Declaring a measure dispensable carries the heaviest documentation burden because skipping a requirement requires written justification to prove it doesn't leave a gap. Visualizing varying asset protection needs as a cityscape, the Grundschutz baseline acts as a horizontal waterline. It covers 80% of typical IT assets, avoiding hundreds of hours engineering custom defenses. However, the organization's crown jewels remain exposed above that baseline, underprotected. An asset falls into this exposed category if it triggers one of three conditions: high or very high protection need, an exotic deployment environment, or no suitable Baustein exists. For these specific peaks, the framework mandates the BSI 203 Ergänzende Sicherheitsanalyse. This is a targeted, deep-dive classical risk analysis applied strictly to the exposed assets. This two-stage strategy is known as the combined approach. It stands in stark contrast to native ISO methods, which demand bespoke risk analysis for the entire landscape, regardless of criticality. The BSI mathematically solves the optimization problem. It deploys rapid, standardized compliance for the mundane 80%, reserving elite risk engineering purely for the critical 20%. Analysis eventually transitions into Realisierungsplanung, or implementation planning, where the missing measures identified in the check are consolidated into an actionable roadmap. Every missing measure requires an explicit deadline and a designated personnel owner to move from a conceptual goal to an actionable requirement. But there is a crucial psychological directive for daily operations. Security must be understood by staff, not merely decreed. If you implement security as a rigid daily operational blockage, you generate friction. And in IT, friction forces users to carve out unauthorized workarounds to get their jobs done. The IT-Grundschutz methodology operates as a